Preparing for a laser systems engineering interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What are the main subsystems of a laser system, and how do they interact? A laser system converts pump energy into coherent optical output through a gain medium inside a resonant cavity. I describe it as 5 coupled subsystems: pump, gain medium, cavity optics, thermal management, and controls. The mirrors set feedback and output coupling, while alignment and cooling determine beam quality and lifetime. In engineering work, I track optical, electrical, thermal, and safety interfaces together, because a weakness in one quickly degrades total system performance. While answering, focus on the gain medium, pump source, optical cavity, mirrors, output coupler, cooling, power supply, and control electronics, and explain how each affects stability, efficiency, and beam quality. Question 2. How would you choose the right laser source for a material processing application? I start from the material and process physics, not the laser catalog. For cutting metals, wavelength affects absorption and coupling. Fiber lasers at 1 micron are efficient for many metals, while CO2 lasers couple well to organics and some non-metals. Pulse duration controls heat-affected zone. Nanosecond can ablate, picosecond or femtosecond reduces thermal damage. Then I balance power, beam quality, delivery optics, maintenance, and cost against the required throughput. Make sure to cover material absorption, required interaction mechanism, wavelength, pulse duration, average power, peak power, beam quality, delivery constraints, efficiency, maintenance, and cost trade-offs for production versus laboratory systems. Question 3. What does m² mean, and why is it important in laser system design? Beam quality is captured by m², which compares a real beam to an ideal Gaussian, and m2 of 1 is diffraction limited. Higher values mean the beam diverges more or focuses to a larger spot. I would measure waist size and divergence using a beam profiler and ISO-style caustic method. For applications like welding or micromachining, m2 directly affects power density, depth of focus, and process repeatability, so it is not just an optics metric. In your answer, talk about m², Gaussian beams, waist size, divergence, focusability, measurement with beam profilers, and why beam quality changes process performance, coupling efficiency, and depth of focus. Question 4. Explain thermal lensing. How would you identify and reduce it in a high-power laser? Thermal lensing happens when absorbed pump or laser power creates a temperature gradient in the gain medium or optics, changing refractive index and physically deforming surfaces. The beam then sees an unintended lens. I look for power-dependent focus shift, mode instability, or reduced coupling. Mitigation includes better cooling geometry, lower absorption coatings, larger mode volume, adaptive optics, or operating below a thermal threshold. Ignoring it often turns a stable benchtop laser into an unstable production tool. Be sure to mention heat generation, refractive index gradients, optic deformation, power-dependent focal shifts, unstable resonator behavior, cooling design, low absorption materials, and how thermal effects limit scaling to higher powers. Question 5. Walk me through your approach to aligning a free space laser beam path. The safe method is low power, blocked paths, and 1 degree of freedom at a time. I first verify mechanical references, optic orientation, and beam height. Then use irises or targets to define the desired path. I align near and far field, so the beam is both position correct and angle correct. For resonators, I make small mirror adjustments, while monitoring output, mode shape, and stability. I never chase maximum power without checking clipping and back reflections. While answering, focus on safe low-power alignment, reference irises, near-field and far-field checks, minimizing degrees of freedom, avoiding clipping, monitoring mode shape, and documenting final alignment settings. Question 6. What laser safety controls would you implement for a Class 4 laser system? Laser safety starts with identifying the class, wavelength, accessible power, pulse energy, and maximum permissible exposure. Controls should follow the hierarchy: enclosure and interlocks first, then beam dumps, key switches, warning indicators, procedures, and eyewear. I calculate optical density for the actual wavelength and exposure scenario, not by guesswork. I also care about invisible beams, specular reflections, fumes, high voltage, and stored energy. A safe system is engineered, not just labeled. Make sure to cover laser class, wavelength-specific eyewear, maximum permissible exposure, nominal hazard zone, interlocks, beam dumps, enclosures, warning indicators, high voltage hazards, fumes, reflections, and administrative controls. Question 7. How do continuous wave and pulsed lasers differ in behavior and applications? Continuous wave lasers deliver steady power, so they are good for heating, welding, communication, and applications needing stable average intensity. Pulsed lasers concentrate energy into short bursts, creating high peak power for ablation, marking, nonlinear optics, or range finding. I compare average power, pulse energy, repetition rate, duty cycle, and pulse width. The same average power can behave very differently thermally. The choice depends on whether the process needs sustained heat or instantaneous intensity. In your answer, compare average power, peak power, pulse energy, repetition rate, thermal effects, material interaction, and application examples such as welding, marking, ablation, communication, and sensing. Question 8. Why is diode pumping commonly used in modern solid-state lasers? Diode pumping is usually more efficient and compact because the pump wavelength can be matched to absorption bands of the gain medium. Compared with flash lamps, it reduces waste heat, improves lifetime, and enables better power modulation. The trade-off is diode cost, wavelength drift with temperature, and the need for good coupling optics. In design reviews, I check pump brightness, absorption length, thermal load, redundancy, and serviceability, because pump architecture drives reliability. Be sure to mention pump absorption, wall plug efficiency, heat load, brightness, coupling optics, diode temperature control, wavelength drift, lifetime, redundancy, and why diode pumping replaced flash lamps in many systems. Question 9. How would you design a feedback control loop to stabilize laser output power? I would separate fast optical control from slower thermal and supervisory control. A photodiode can sample output power, then a PID loop adjusts pump current or an attenuator to hold set point. Temperature loops stabilize diodes, crystals, and optics to prevent wavelength and alignment drift. I also log faults, interlocks, and calibration data. The key is loop bandwidth. Make it fast enough to reject disturbances, but not so aggressive that it oscillates or amplifies noise. While answering, focus on photodiode feedback, pump current modulation, attenuators, PID tuning, temperature stabilization, loop bandwidth, noise, calibration, fault logging, and how controls protect both performance and safety. Question 10. A laser system suddenly loses 30% output power. How would you troubleshoot it? I would troubleshoot from measurement outward. First, I confirm the power meter calibration, wavelength setting, and sampling location. Then I check obvious losses: dirty optics, clipping, misalignment, damaged coatings, and back reflections. Next, I inspect pump current, diode temperature, cooling flow, interlocks, and cavity stability. If power drops with beam quality changes, alignment or thermal lensing is likely. If pump power also falls, the electrical or thermal subsystem becomes the suspect. Make sure to cover a structured diagnostic flow. Validate measurement, inspect optics, check alignment, evaluate pump health, cooling, interlocks, contamination, thermal drift, beam quality, and recent configuration changes. Question 11. What are coherence and linewidth, and where do they matter in laser systems? Coherence describes how predictably the optical field maintains phase over time and space. Temporal coherence relates to linewidth and coherence length. Spatial coherence relates to how well the beam can be focused or interfered. Narrow linewidth matters in interferometry, spectroscopy, coherent communications, and LiDAR. In practice, I think about cavity length, mode selection, frequency noise, temperature stability, and feedback isolation. High coherence is powerful, but it can increase speckle and sensitivity to reflections. In your answer, talk about temporal and spatial coherence, linewidth, coherence length, cavity modes, frequency stability, interference applications, speckle, and why coherence can be beneficial or problematic. Question 12. What is the difference between Q switching and mode locking? Q switching stores energy in the gain medium by holding cavity losses high, then releases it as a short, high-energy pulse when the cavity Q is restored. Mode locking forces longitudinal modes to maintain fixed phase, producing ultra-short pulses with high peak power. I associate Q switching with nanosecond marking or ranging, and mode locking with picosecond or femtosecond micromachining and spectroscopy. The design choices differ: energy storage and damage limits versus dispersion, timing jitter, and bandwidth. Be sure to distinguish energy storage from phase locking, covering pulse width, peak power, repetition rate, longitudinal modes, saturable absorbers or modulators, dispersion, timing jitter, and application fit. Question 13. How do you select optical coatings for high-power laser optics? Coatings are not just reflectivity numbers. They determine loss, heating, polarization behavior, dispersion, and damage margin. I specify wavelength, angle of incidence, polarization, bandwidth, environment, and expected fluence or irradiance. For high-power lasers, low absorption and contamination control are critical because tiny defects become hotspots. I also consider cleaning process and handling. A cheap coating can cost more than a premium one if it limits uptime or damages downstream optics. While answering, focus on coating reflectivity or transmission, wavelength range, incidence angle, polarization, absorption, scatter, laser-induced damage threshold, contamination sensitivity, cleaning limits, and thermal loading at high power. Question 14. When would you use fiber delivery instead of free space beam delivery? Fiber delivery improves packaging, routing, and integration with scanners or robots, especially for industrial fiber lasers. It can make the machine more robust and easier to service. Free space delivery gives more flexibility for unusual wavelengths, ultra-short pulses, high pulse energies, or sensitive polarization control. I evaluate numerical aperture, bend radius, connector damage, back reflection, nonlinear effects, and end cap power density. The best choice is application-driven, not automatically fiber, because it is convenient. Make sure to cover alignment robustness, packaging, numerical aperture, bend radius, connector damage, nonlinear effects, polarization preservation, back reflections, wavelength compatibility, high peak power limits, and service trade-offs. Question 15. How would you translate customer requirements into a complete laser system design? I would turn the process goal into measurable optical requirements: wavelength, power or pulse energy, spot size, beam quality, stability, duty cycle, and working distance. Then I design the source, beam delivery, cooling, controls, enclosure, and safety around those numbers. I include diagnostics early: power monitoring, temperature sensors, interlock status, and beam verification. Finally, I define acceptance tests for output, pointing stability, repeatability, and safety compliance. Good systems engineering prevents late surprises. In your answer, talk about converting application goals into optical, electrical, thermal, mechanical, control, safety, reliability, and test requirements, then validating them through measurable acceptance criteria. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.